In section 6.4, we introduced the concept of parametric equations. First, I want to go over something that we've talked about previously, and that is the unit circle. So on the screen here, you see a picture of the unit circle with all of the associated special angles within that circle. Now, when we first introduced the unit circle, we talked about how the x-coordinate on the unit circle is the cosine of the angle associated with that point, and the y-coordinate is the sine of the angle associated with that point. But if we look at this in a different way, we could have started with the premise that x is equal to the cosine of some variable t and y is equal to the sine of some variable t. And we know that cosine squared of t plus sine squared of t is equal to 1. And if we know that cosine of t is equal to x, then cosine squared of t would simply be x squared. And if sine of t is equal to y, then sine squared of t would be y squared. And we notice that if we had just started with these two equations, this would have led to the unit circle. Now, I know it might seem like the same thing, but remember, previously we started with the unit circle and then we brought the trig functions into it. But we could have started with these two equations and gotten the unit circle from it. So what we've done here is we have come up with what are called parametric equations that describe the unit circle. And in these parametric equations, t, the independent variable t, is what we call the parameter. And if you look at the graph, you'll notice that the graph has points that have x and y coordinates, but the variable t need not be associated with the graph at all. So this third variable, this parameter, if you will, is a sort of invisible variable. So parametric equations give us another way to think about graphs in the coordinate system. And the nice thing about parametric equations is that you can separate the x and y variable from each other and express them in terms of a third independent variable, again, that we call the parameter. Let's take a look at an example. Suppose I give you the parametric equations x equals 3 times the cosine of t and y equals 2 times the sine of t. And what I want you to do is eliminate the parameter t from these parametric equations. In other words, can you write a single equation involving only x and y? And if so, how would you do this? Well, remember the Pythagorean identity. Cosine squared of t plus sine squared of t is equal to 1. Well, we don't have cosine of t and sine of t isolated, but we certainly could isolate each of those in these parametric equations. So in the first parametric equation, x equals 3 cosine of t, we can solve for cosine of t by simply dividing both sides by 3. And if we do this, we end up getting cosine of t equals x over 3. And in the second equation, y equals 2 times the sine of t, we can divide both sides of that equation by 2, and that will give us sine of t is equal to y over 2. Now keep in mind that cosine squared of t is actually cosine of t quantity squared, and sine squared of t is sine of t quantity squared. But since we know that cosine of t is x over 3, we can put that in here. And since sine of t is y over 2, we could put that in here. And in doing so, we get x over 3 quantity squared plus y over 2 quantity squared is equal to 1. And if we remove the parentheses, we end up with x squared over 9 plus y squared over 4 is equal to 1. And we now have a rectangular equation relating x and y without the parameter t. So basically, we have eliminated t. Now, what does this equation look like when you graph it? Well, if you remember from intermediate algebra, this equation, when graphed, is what we call an ellipse. And let's go ahead and bring in a picture of what that would look like. And so here is what that graph looks like. And I won't talk too much about the equation of ellipse and how you graph it, as this is stuff that you have probably learned before. But basically, we have a set of points that are described from this equation. But our original parametric equations were x equals 3 cosine of t and y equals 2 sine of t. These parametric equations describe the same set of points. Now, I do want to talk about one major difference between the rectangular equation that you see here and the parametric equations that you see here. The rectangular equation simply gives you the set of points, and that's it. But the parametric equations give you a little bit more. Suppose we considered a table of values where we have the parameter t here, and then we have 3 times cosine of t here, which is the x variable, and 2 times the sine of t here, which is the y variable. And I want you to notice the values that we get for each of these. If we plug in t equals 0, t equals pi over 2, pi, 3 pi over 2, and 2 pi. Now, I won't go through all the math on each of these, but let's go through a couple. So if t equals 0, we know that the cosine of 0 is 1, and 3 times 1 would be 3. And if t equals 0 here, sine of t would be 0, right? Because sine of 0 is 0. And multiplied by 2, that would still be 0. And so that gives us the point x equals 3, y equals 0. If t equals pi over 2, the cosine of pi over 2 is 0. And the sine of pi over 2 is 1, and 2 times 1 would be 2. And that gives us the point 0, 2. Now, if you keep on going through and doing this, you will end up getting the following points. And what's nice about this is there is a definitive order to the points that we're getting. So in other words, when t was equal to 0, that gave us this point right here. And when t was equal to pi over 2, we got this point here. T equals pi gave us this point over here, and t equals 3 pi over 2 gives us this point, and then t equals 2 pi brings us all the way around back to this point. So notice that as t increases, there is a definite orientation to this curve. We are moving in this direction. And this is the nice thing about parametric equations. They don't just give you a set of points. They give you an orientation to the curve. Now, I also want you to notice that if you were to plug in more values of t that were bigger than 2 pi, you would simply continue to move around this curve as t increases. So parametric equations are kind of interesting because even though they give you the same set of points, they also give you a little bit more information. In this next example, we want to go ahead and do the same thing, eliminate the parameter t from the equations. So in the first equation, we have x is equal to 3 plus the sine of t. So what I can do here is subtract 3 from both sides, and that will give us x minus 3 equals the sine of t. In the second equation, we have y equals cosine of t minus 2. And so if I add 2 to both sides, we end up getting y plus 2 is equal to cosine of t. And now let's remember that sine squared of t plus cosine squared of t is equal to 1. And again, that is sine of t quantity squared plus cosine of t quantity squared equals 1. But then we see that sine of t is x minus 3, and cosine of t is y plus 2. And so if we plug those into the equation here, we get x minus 3 squared plus y plus 2 squared is equal to 1. And this is the equation of a circle, and the center of this circle is x equals 3, y equals negative 2, and the radius of this circle is equal to 1. Now, if I bring in a graph of that circle, it's going to look like this. And so here you see we have a circle with a radius of 1 unit, and the center of that circle is at x equals 3, y equals negative 2. Now that is the set of points, and that's all you really need to know how to do in this section. But if we get back to the additional information that the parametric equations give you, I just want to talk briefly about the orientation of this curve. So here are our original parametric equations. I'm going to select values of t, that is, from 0 to 2 pi. So I'll use the same values for t that we used in the last example. And if we plug those in, if t equals 0, sine of 0 is 0, and we get 3 plus 0 is 3. And if t equals 0 here, cosine of 0 is 1, and 1 take away 2 is negative 1. And if I plug in pi over 2, sine of pi over 2 is 1, plus 3 is 4. And the cosine of pi over 2 is 0, take away 2 is negative 2. At pi, sine of pi is 0, so we end up getting 3. Cosine of pi is negative 1, so we get negative 3. And at 3 pi over 2, we will get 2 here and negative 2 here. And finally, at 2 pi, we will get 3 and negative 1 again. And those are the points 3, negative 1, which is right here. Okay, so this is when t equals 0. And then we have the point 4, negative 2, which is this point right here. And that occurs when t equals pi over 2. And then 3, negative 3 is this point, which occurs when t equals pi. And then we get 2, negative 2, which is when t equals 3 pi over 2. And finally back to this point up here when t equals 2 pi. So I want you to notice that the curve starts here and traces out in this direction. So again, when you have a set of parametric equations, you not only get a set of points, but you also get an orientation to that curve. And if you have a specific range of values here, you get a starting point and an ending point to that set of points. So just something to keep in mind as you move forward. In our next example, we have x equals 3 plus 2 times the secant of t, and y is equal to 2 plus 4 times the tangent of t, and we want to eliminate the parameter. So I'm going to start by subtracting 3 from both sides in the first equation, and then I can divide both sides by 2. And in the second equation, I can subtract 2 from both sides, and then divide by 4. And that allows us to solve for secant and tangent. Now, to eliminate the parameter, we need to have a relationship between secant and tangent, and we do. We know that secant squared of t minus tangent squared of t is equal to 1. Now, we don't normally state this identity in this way. You might remember that what we normally do is we say 1 plus tangent squared is equal to secant squared. But if I subtract tangent squared from both sides, you can see that we end up getting this identity here. But again, we know that secant of t is x minus 3 over 2, so we can take this expression and put it in for secant. Tangent of t is y minus 2 over 4, we can put that in here. And in doing that, we end up getting x minus 3 over 2 quantity squared minus y minus 2 over 4 quantity squared is equal to 1. And if you write this a little bit differently, we can say x minus 3 squared over 4 minus y minus 2 squared over 16 is equal to 1. And this is the rectangular equation that describes the same set of points. Now, I don't know if you remember or not, but this is what we call a hyperbola. And I'll bring in a graph to remind you of what that looks like. So here is what that graph looks like. We have a center right here, and that center would be at x equals 3 and y equals 2. So I'll go ahead and put that in here. And then I won't talk about how to graph a hyperbola here because, again, this is something that is covered in algebra classes, but you can see that we have the set of points right here. This is the hyperbola. You get this very unique looking graph. So again, in this section, we mostly just want to focus on if you're given a set of parametric equations, how do you eliminate the parameter? And so you might have noticed in the past 3 examples that the way that we do that is we use trig identities to help us eliminate those parameters. Now in our final example here, we're going to look at an application of parametric equations. And here it says a human cannonball leaves the cannon 88 feet per second, which is approximately 60 miles per hour. If theta is the angle the cannon makes with the horizontal, then the position of the cannonball, xy, can be given by the parametric equations that you see here. The first equation gives the horizontal distance the cannonball has traveled after t seconds, and the second equation gives the vertical position of the cannonball after t seconds. All right, so let's first make sure we understand the situation. So what we have is a human cannonball. So here is the cannon, and we'll put that at the origin of the x and y axis. This person is fired into the air and travels until they land in a net. And the net is set up at the same height as the starting point of the person. Now, if you would like to know where is that person at any given time, that can be given by the point xy. Now, x represents this horizontal distance that you see here, and y represents the vertical distance that you see here. And t is time, right? So as the person is fired into the air, time is ticking by in seconds, right? So if I want to know the horizontal distance the person has traveled at any given time, I can use this equation. And you'll see that t stands for time and is in that equation there. If I want to know the vertical height that the person is at any particular time, I can use the second equation. And so in terms of the graph, notice that you do not see the variable t at all in this graph. It's nowhere to be seen physically. The only thing you can see is the human cannonball traveling through the air, and you can see the horizontal distance that has been traveled and the vertical distance that has been traveled. So this parameter t, which stands for time, is invisible. All right, now let's talk about the questions that they ask. So the first question says, if theta equals 30 degrees, how long will the cannonball be in the air before landing on the net? All right, so first of all, if theta is 30 degrees, we need to figure out what these equations would look like. So the first equation would be x is equal to 88 times the cosine of 30 degrees times t And the second equation would be y equals 88 times the sine of 30 degrees times t, and then minus 16 times t squared. Now let's remember that cosine of 30 degrees is the square root of 3 over 2, and the sine of 30 degrees is 1/2. And so in the first equation, we're going to have 88 times the square root of 3 over 2 times t. And this is 44 radical 3 times t. And in the second equation, we have 88 times 1/2 times t, and then minus 16t squared. And this is equal to 44t minus 16t squared. And this gives the height of the cannonball at any time t. Now, to answer the question, how long will the cannonball be in the air before landing on the net? I want you to notice that when the person lands on the net at this point here, y is equal to 0. We don't know what x is at that point, right? We don't know how far this person's going to travel, but we do know the height of that person will be 0 again because they are landing on that net, which is at an original height of 0. So to answer this question, we just need to solve for when is y equal to 0. When does that happen? Well, if y equals 0, I can plug in 0 for y into this equation, right? Because remember, this equation says y equals this amount. So if y equals 44t minus 16t squared, this is going to give us 0 equals 44t minus 16t squared. And we could solve this by factoring. We can pull out a 4t. And if we do that, we get 11 minus 4t. Verify that. And then we can set each one of those factors equal to 0. Solving the first equation, we get t equals 0. Solving the second equation, we get t is equal to 11 divided by 4. And 11 divided by 4 is 2.75. There we go. And so the question is, how long will the cannonball be in the air before landing? Well, there's two possible answers. Either it's 0 seconds, which doesn't make any sense, right? Because 0 seconds means that the person hasn't even been fired into the air yet. So it can't be this answer. The other answer is 2.75, and that seems to be the correct answer. Now, why is 2.75 seconds the right answer? Well, because again, the human cannonball is at 0 at 2 times. It's at 0 right here, and this is at the beginning when t equals 0. And it's at 0 here when t equals 2.75. So this time here is the landing time. All right, let's take a look at the second part of the question. For the second question, it says, graph the second equation when theta is 30, when theta is 45, when theta is 60. So the second equation, and use t for the horizontal axes and y for the vertical axes. All right, so the second equation, remember, is y equals 88 sine of theta times t minus 16t squared. And so if theta is 30 degrees, we know that y is going to be 44t minus 16t squared. We already talked about that one in part A. If theta is equal to 45 degrees, then what we get is y equals 88 times the sine of 45 degrees times t minus 16t squared. And this is 88 times the square root of 2 over 2 times t minus 16t squared. And that is 44 radical 2t minus 16t squared. So this is what we get if theta equals 45 degrees. And then finally, if theta equals 60 degrees, y is going to be 88 sine of 60 degrees times t minus 16t squared. And this is 88 times the square root of 3 over 2 times t minus 16t squared. And that becomes 44 radical 3 t minus 16t squared. So you'll see we have three different equations for y and t, depending on the angle. Now let's take a look at those graphs. And I'm just going to bring in a picture of the graphs. I'm not going to take the time to show how to graph each one of these. I will just say that each one of these is a quadratic function. So the picture should be a parabola. And the parabola should be opening downward because we have a negative coefficient in front of t squared. Let's take a look at the graphs. All right, so here is a picture of the graphs. The first graph here represents when theta equals 30 degrees. This graph here represents when theta equals 45 degrees. And finally, this graph here represents when theta is 60 degrees. And you'll notice that the steeper the angle that the person is fired at from the cannon, the higher the cannonball will go into the air. So you can see that when theta is 30 degrees, the maximum height of the cannonball appears to be about 30 feet into the air. But if we change the angle of the cannon to 45 degrees, now the person's going to reach a maximum height of about 60 feet. And finally, if you change the angle of the cannon to 60 degrees, now the person's going to reach a maximum height of about 90 feet. And the cannonball will stay in the air longer. So at theta equals 30, the cannonball is going to land 2.75 seconds later. At theta equals 45, it's going to land at almost 4 seconds later. And when theta is 60, it's going to land at close to 5 seconds later. So the steeper the angle of the cannon, the longer the human cannonball stays in the air. So the nice thing about this example is that it shows you an application of parametric equations. So remember, what we have here is two equations, both defined by the variables x and y being equal to some function of the variable t, right? And in this problem, the variable t represents time. And that time is, again, invisible when you're talking about the original graph of the path of the human cannonball. But it also brings into the problem some really important information, because the whole time this human cannonball is in the air, there is that third variable, time, is ticking away, right? And so this is just a quick example of how parametric equations can be useful.